Hi everyone. So in this lecture we are going to discuss applications of adsorption. In the last two lecture we have discussed the adsorption isotherm, that is a Freundlich adsorption isotherm, and the Langmuir adsorption isotherm. So here when we consider the applications of the adsorption, there are number of applications of the adsorption. In today's lecture, we are going to discuss some important application of the adsorption. So, let us consider one by one. So, here the first application is catalysis. The phenomenon of the adsorption, generally it is used in the catalysis. So, all of you know that catalysis is a process in which the catalyst is used to carry out the chemical reaction. So, here when we consider the catalysis, there are two types of the catalysis: heterogeneous catalysis and the homogeneous catalysis. Generally in the homogeneous catalysis, the reactant and catalyst, they are present in the same phase, while in case of the heterogeneous catalysis, the reactants and catalyst, they are not present in the same phase. So here the phenomenon of the adsorption, generally it is used in the heterogeneous catalysis. So here there are many reactions between the gaseous substances which takes place in the presence of the solid catalyst. Generally here when we consider the catalysis or the heterogeneous catalysis, the catalyst is present in the solid state. So here such types of the reactions falls under the category of the heterogeneous catalysis. Here the catalyst functions by adsorption of the reactant molecule on its surface, and here the surface reaction can usually broken into the following step. So generally here the reactants are adsorbed on the surface of the catalyst. So here the phenomenon of the adsorption is used in case of the catalysis. So let us consider one example of general chemical reaction. Here the A gas, it react with the B gas. So here the A and B gases are the reactant, while the C gas and D gas are the products. So here this is the catalyst, and generally it is present in the solid state. So here this reaction takes place in the 4 steps. So let us consider one by one. The step number 1 is adsorption of the reacting substance on the surface of the catalyst. So here the reacting molecule A and B collide the catalyst surface. So here they are adsorbed on the surface of the catalyst, and here they are held at the active centers on the surface of the catalyst by the weak van der Waals forces, that is the physical adsorption, or by the partial chemical bond, that is the chemisorption. So here this is the step number 1, that is the adsorption of reacting substance on the surface of the catalyst. So here number 1. Then the second step is formation of the activated complex. This is the second step. So here the adsorbed reacting molecule may then combine to form the adsorbed activated complex AB. So here these reacting gas molecules are adjacent to one another and are joined to form activated complex on the surface of the catalyst. So here there is a formation of the adsorbed activated complex between the two reactant A and B. This is the step number 2, and here this process, that is the formation of the activated complex, it took place on the surface of the catalyst. So this is the second step. Then the third one is chemical reaction on the surface. So here the activated complex decomposes during the chemical reaction on the surface to form the product C and D. So here on the surface of the catalyst there is a formation of the product. So here the decomposed products are held up at the surface by the partial chemical bond. So here C and D are the product, and here there is a formation of the product on the surface of the catalyst just by breaking the activated complex. So this is the step number 3, and here the step number 4, desorption of the product from the surface. That means here the product C and D, they are removed from the surface of the catalyst. This is the step number 4. So here desorbed product C and D. So here the products molecule C and D are desorbed from the surface. So here the diffusion of the products away from the catalyst surface takes place, and the products are stable. So here C and D are the product. So here the products are released from the surface. They can lead an independent existence. So here the step number 4. So in this way the catalysis, the phenomenon of the adsorption is used. A and B are the reactant, and from the A and B they are converted into the C and D by using the four steps. So friends, here it has been found that there are some active centers are present on the surface of the catalyst. So here when we consider any solid catalyst, number of active centers are present on the surface of the catalyst, such as the peaks, cracks, corner, furrows, edges. So these are the active centers, and here where the adsorption takes place. The catalytic activity due to the adsorption of reacting molecules is maximum at the active centers. The active center increase the rate of the reaction by increasing the concentration of the reactant on the surface and activating the adsorbed molecule at two such center by the stretching it. So here the first application of the adsorption, that is the catalysis. Let us consider second application. Second application is in purification of the water. If we have to purify the water, the phenomenon of the adsorption is used. Friends, generally all of you know that naturally occurring water, mainly it contains the two types of the impurities, that is the soluble impurity as well as the insoluble impurities. So which are the insoluble impurities? So insoluble impurities are the clay, sand, vegetable matter. And which are the soluble impurities? Soluble impurities are salts of the metals like sodium, calcium, magnesium, iron, etc. That means here when the salt is present in the water, it is a soluble in the water. So such impurity, it is called the soluble impurity. So here what we have to do? We have to remove the insoluble impurity as well as the soluble impurity. So here insoluble impurities just they are removed by the filtration. So here we have to filter the water. When we filter the water, insoluble impurities such as the clay, sand and vegetable matter are removed from the water. Then the question is how to remove the soluble impurities from the water. So here for that purpose the phenomenon of the adsorption is used. So here the filtered water. So here when we filter the water, insoluble impurities are removed. So here the filter water is then passed through the finely divided charcoal packed in the column. In the column there is a charcoal, and here the filter water is then passed through the finely divided charcoal. The charcoal is good adsorbent. So here the number of active centers are present on the surface of the charcoal. So that's why here the charcoal is act as the good adsorbent. So here it adsorbs the soluble impurity together with the vegetable and the other coloring matter. The presence of the soluble impurities makes the water hard. So here if the soluble impurities are in the water, such water is called as the hard water. It is not soft water, it is hard water. And here the hardness of the water, it is due to the presence of mainly the calcium 2 plus ion and the magnesium 2 plus ion. If these cations are present in the water, then such water is the hard water. Some natural silicates like zeolite and some synthetic organic long chain compound called as the resin. So here this zeolite and the resin, they have the tendency to adsorb the H plus ion. When such zeolite or when such resins, when they are treated with the acids, they adsorb the H plus ions, or when they are treated with the alkali, they adsorb the OH minus ion. So here there are two types of the resins, that is the cation exchange resin as well as the anion exchange resin. So here the cation exchange, it adsorbs the H plus ion, and the anion exchange, it adsorbs the OH minus ion. So here the cation exchange resins are first treated with the dilute acid. So here when the cation exchange resin, when they are treated with the dilute acid, it adsorbs the H plus ion from the acids. Then here the anion exchange resins are treated with the dilute alkali. So here the OH minus ions of alkali get adsorbed by these resins. So here the cation exchange and anion exchange resins are then washed several times to remove the excess of the acid or the alkali. So friends, here there are two types of the resin, cation exchange resin and the anion exchange resin. Cation exchange resin, first it is treated with the dilute acid, it adsorbs the H plus ion. Anion exchange resin, first it is treated with the dilute alkali, it adsorbs the OH minus ion. So here these proceed cations and anion exchange resins are further used to remove the calcium 2 plus, magnesium 2 plus cations as well as the Cl minus and the SO4 minus anions from the hard water. When ions like calcium 2 plus or magnesium 2 plus from the hard water, when they come in contact with the cation exchange resin, what happen? So here the H plus ion exchange calcium 2 plus ion or magnesium 2 plus ion. So here the calcium 2 plus ion and magnesium 2 plus ions get adsorbed by the resin. Such ion get adsorbed by replacing the 2H plus ion. So here when the calcium 2 plus ion is adsorbed on the cation exchange region, here there is a replacement of the 2H plus ion, or here when the magnesium 2 plus ion it adsorbed on the cation exchange region, at that time there is a replacement of the 2H plus ion. Similarly, OH minus ion from the anion exchange region get exchanged for the Cl minus or the SO4 minus minus ion. So here the Cl minus or SO4 minus minus ion get adsorbed by the region, thus water is softened and this water is called as the demineralized water. So here friends, when we consider the insoluble water, impure water, then impure water it contains the two types of the impurities, that is the soluble impurities as well as the insoluble impurities. So insoluble impurities are removed by just filtration, while the soluble impurities are removed by using the phenomenon of the adsorption. For that purpose, here we have to consider the cation exchange region as well as the anion exchange region. In this way, the hard water may be softened with the help of the phenomenon of the adsorption. Then the third application of the adsorption is production of the high vacuum. So gases gets more easily or readily adsorbed on the solid at low temperature. So here the considerable adsorption at low temperature, even at the low pressure, is utilized in the production of the high vacuum. In any system or in any apparatus, if we have to produce or high vacuum, or if we want high vacuum in such apparatus, for that purpose here the phenomenon of the adsorption is used. So here the coconut charcoal is used as the adsorbent. So here the coconut charcoal cooled in the liquid air is an efficient adsorbent. So here it is connected to the apparatus which has already been first evacuated as far as possible by the vacuum pump. So here in the apparatus or in the system in which we have to produce high vacuum. So here such apparatus or such a system, first of all it is connected to the vacuum pump, and with the help of the vacuum pump, whatever air or whatever moisture is present such apparatus or such a system, it is taken away, and then such apparatus it is treated with the coconut charcoal. So here the charcoal adsorbs remaining gases and the moisture almost completely and thus created the high vacuum. So here by using the phenomenon of the adsorption, here in the apparatus or in the system, high vacuum is created. So this is the third application of the adsorption. Then next one is the adsorption indicator. So let us consider next one, adsorption indicators. The phenomenon of the adsorption, it is useful to determine the end point in case of the precipitation titration. So here what is meant by precipitation titration? The titration in which one of the product it is in the form of the precipitate. So here in a precipitation titration, if we have to determine the end point, the phenomenon of the adsorption used by using the adsorption indicator. So let us consider one example of the precipitation titration, that is a titration between the sodium chloride and the silver nitrate. So here in presence of the bromocresol blue is an example of the such types of the titration. So here the bromocresol blue has colored anion in it. When silver nitrate solution is added gradually to the solution of the sodium chloride, generally here the silver nitrate solution it is taken in the burette, while sodium chloride it is taken in the conical flask, and here the bromocresol blue it is used as the indicator. So here there is a formation when we add the silver nitrate in the sodium chloride, it is a precipitation reaction or it is a precipitation titration. There is a formation of the silver chloride precipitate. So here after complete precipitation of the silver chloride, so here when we add the silver nitrate into the sodium chloride, there is a formation of the silver chloride as well as the sodium nitrate. So here after completion of the precipitate of the silver chloride, any further addition of the silver nitrate will increase the concentration of the silver ion in the solution. The silver chloride now adsorbs the colored anion of the indicator from the solution. So here when we consider the indicator bromocresol blue, so here bromocresol blue it has the colored anion. So here such a colored anion it adsorbed by the silver chloride. So here the change in color of the precipitate is the end point of the titration. So here the silver chloride in solution in presence of the excess of the chloride ion, the stage before the equivalence point of the titration. So, what is the situation in the conical flask before the equivalence point? So, here there is a precipitate of the AgCl, and here there is a excess Cl minus ion. The precipitate of the AgCl, it is covered with the Cl minus ion, and which is a negatively charged, and this cannot attract or this cannot attach the anion of the indicators to the themselves, but as the concentration of the silver ion increases. So, at the stage after the equivalence point, so here after the equivalence point, what happen? Whatever Cl minus ions are present in the solution, all the Cl minus ion they combine with the Ag plus ion, and there is a formation of the AgCl. So, after the equivalence point in the conical flask, there is no Cl minus ion, and here when we add the excess AgNO3 from the burette, so here the precipitate of the AgCl, it is covered with the Ag plus. So, here the particle of the precipitate becomes positively charged because there is an excess of the Ag plus ion. This immediately absorb the colored anion of the indicator, and here there is a change in the color of the solution. That means here the end point is obtained. So, here in this way the phenomenon of the adsorption, it is used to detect the end point in the precipitation titration by using the adsorption indicator. So, here we have considered one example, that is a titration between the AgNO3 and the sodium chloride. So, number of precipitation titrations can be studied with the help of the phenomenon of the adsorption, and we can use the various indicator to detect the end point in such titration. Here the dyestuffs such as the eosin, fluorosin, etc. are also used as indicator in such titration. Then the next application of the adsorption is the chromatography. So, here all of you know that the chromatography, it is a separation technique. So, here this method this is a method to separate the constituent of a mixture, and is based on the fact that the substances can be selectively adsorbed from the solution by a given adsorbent. So, here in the analysis, a solution of mixture in suitable solvent. So, here first we have to prepare the solution of the mixture, and the suitable solvents are acetone, benzene, alcohol. The solvents are used to prepare the solution of the mixture. Then here such a solution is allowed to flow through the long tube filled with the adsorbing solid. So, here in the long glass tube, it is filled with the adsorbing solid such as the alumina, magnesium oxide or the silica gel. So, here alumina, magnesium oxide or the silica gel, they are filled in the long glass tube such as the adsorbing solid. So, here after passing the mixture through the adsorbing solid, it is observed that the upper layer consider mainly of the solute that is the most easily adsorbed by the adsorbent, together with the small amount of less readily adsorbed solute. So, here the less readily adsorbed substances gradually adsorb lower down the column as they pass through the column. So, here in the column, in the upper portion of the column, here the substance which is easily adsorbed, it adsorbs first, and at the lower part of the column, the substance which is not easily adsorbed, it is adsorbed at the bottom of the column. So, here the less readily adsorbed substances gradually adsorb lower down the column as they pass it through the column. Some amount of the pure solvent is allowed to flow slowly through the column. The less readily adsorbed solutes are removed from the upper part of the column, and successive layer of the column contain other constituent in order of their ease of adsorption. When separation is completed, the adsorbent column is pushed out the tube and cut into the section, that is from the column the adsorbent is taken away, or it is taken out and it cut into the smaller sections. The adsorbed constituents from the sections are then dissolved by using the suitable solvent. Alternatively, the large amount of the solvent is allowed to pass through the column. The less strongly adsorbed substance will push down the column and is collected at the bottom first. the other constituent in order to their ease of adsorption are collected successively at the bottom. So, here in this way we can separate the substances from the mixture by using the phenomenon of the adsorption, and here this is very useful in the chromatographic technique. So, here friends, these are the important application of the adsorption. So, let us consider some other miscellaneous applications of the adsorption. Removal of odor from the thermostat, water bags, refrigerator and air conditioner can be done by adsorption on activated charcoal. So, this is the another application of the phenomenon of the adsorption. The gas mask contain adsorbent. So, here the gas mask contain the granule charcoal. So, granule charcoal is the adsorbent. So, the gas mask contain adsorbent which remove the poisonous gases from the atmosphere and thus purify the gas for breathing. Decolorization of the sugar is done by passing its solution over the animal charcoal. So, here by using the animal charcoal decolorization of the sugar is possible. So, here the phenomenon of the adsorption is used. In manufacture process of the sulfuric acid, generally platinum or the vanadium pentoxide is used as the catalyst in contact process. Similarly, iron powder is also used as a catalyst in manufacture of the ammonia in Born-Haber process. Then here nickel is used in the hydrogenation of oil to ghee. So, here all these manufacturing processes, the phenomenon of the adsorption is used. Adsorption of the gas on the solid surface is important tool to use for the determination of the surface area of the solid in their finally divided form. For the determination of the surface area of the solid, here again the phenomenon of the adsorption is used. Dehydration and purification of the chlorine, nitrogen, carbon dioxide, helium, oxygen etc. is done by silica gel and the alumina. So, here the silica gel and the alumina, they can be used as the adsorbent. Surface active agents are used in the detergent, paints and the lubricant. All surfaces are covered with the layer of the either gaseous liquid or solid films, and these adhering agents are removed by wetting. So, here the wetting agents lower the interfacial tension by the adsorption. Soap and detergents are used as a wetting agent for cleaning process. So, here the soap and the detergent, they are used as the wetting agent for the cleaning process. And the lastly here the ferric hydroxide is a good adsorbent for the arsenic ion. So, here arsenic salts are very poisonous. All of you know that the arsenic salts are very poisonous. So, here the ferric hydroxide is used as antidote in case of the poisoning by the arsenic. So, here in case of the arsenic poisoning, when the ferric hydroxide is used, so ferric hydroxide it adsorbs the arsenic ions. So, here the phenomenon of the adsorption is used. So, these are the some miscellaneous application. So, friends, in this lecture we have discussed some important application of the phenomenon of the adsorptions. Thank you.